Welcome to the Sky Commander Flight Brief. It's your mission-ready podcast for drone pilot training and aerial insights across Canada.
From Transport Canada rules to real-world drone ops, we break it down, take you higher, and help you earn your wings. Because here at skycommander.ca, we don't just fly.
It hints there's more to it. It's a masterclass, a deeper level, maybe a philosophy or a community focus, perhaps.
It's definitely intriguing, sets them apart from just, a basic tips show. Skycommander.ca is the obvious next step. Precisely. If you're thinking about flying a drone in Canada, boom, this content is aimed right at you.
Powered by skycommander.ca.
The elite podcast for Canada's drone pilot. Okay, let's get started.
Today we're tackling one of those critical, yet often misunderstood elements of autonomous aviation. It's that moment the system really has to prove its maturity. So picture this. A drone is operating miles away, completely beyond the operator's eyesight, and it's on a vital mission, maybe inspecting, 50 miles of critical pipeline or delivering medical supplies across a tight urban corridor. Everything's routine, all systems are green, and then the communication link fails. The dreaded lost link scenario.
It is the ultimate litmus test for any beyond visual line of sight or BVLOS platform. It really is. For years, the default response was often just a hard, immediate return to home, RTH. But as these operations scale and move into denser airspace, that simple, almost frantic reflex, it's just not considered safe or predictable or acceptable anymore.
Absolutely. And our deep dive today is designed to take you right into the heart of this evolving regulatory and operational challenge. We're moving far beyond just pressing the RT8 button. You, the listener, you're stepping into the elite architectural review process with us because the FAA's proposed Part 108 rule for routine BVLOS flight is fundamentally forcing operators to design a complete, multi-layered, fail-safe ecosystem.
Exactly. We're pulling insights from, high-level operational training manuals, the regulatory language itself, engineering standards. And the goal here is to show the shift from purely reactive safety, trying to fix a problem as it happens, to predictable, proactive safety, where every single contingency is designed, tested, and automated from the get-go. This is about integrating aircraft design, operator procedures, comms monitoring, ground risk planning, and, of course, comprehensive training.
And here is the core meta principle that ties this whole deep dive together. And it's the one thing I think most people miss. You are not designing a single fail-safe action. You're designing an integrated, multi-layered fail-safe ecosystem. It's a whole system of systems designed to ensure that when that connection fails, the aircraft's behavior does not fail with it. Our mission today is to understand how that predictability is mandated and how it's enforced.
Okay, so let's unpack the system. Let's start with the most fundamental concept, the actual moment of failure. When we talk about lost link, the common assumption is that it's just a binary switch, right? The signal is either perfect or it's completely gone. But you're telling us that in real-world operations, that black and white view is, it's a dangerous simplification.
It is. It's a rookie mistake to assume binary failure. In the real environment, especially with cellular or, radio frequency links that are subject to terrain, interference, and distance, lost link is often intermittent. It's noisy. It's characterized by degraded performance, and that's the critical pro-level insight. The FAA's proposed Part 108 rule explicitly demands that operators address this reality. They flag that intermittent link loss and high latency must be assessed and accounted for in the system design.
So the system can't just wait for a total dead silence before it reacts. It needs to manage the transition into failure.
Precisely. We're talking about designing for graceful degradation, not a sudden cliff-edge failure. And this means our training protocols have to address a whole spectrum of failure states. First, you've got those micro dropouts link losses that last maybe only a few seconds. Second, you have degraded link conditions, which are characterized by high latency, substantial packet loss. The aircraft is getting commands, but with a huge delay, or it's missing telemetry. And then third, you have the hard loss link, which is the full timeout trigger. Safety is built by managing the hysteresis between these states, making sure the aircraft doesn't thrash or overcorrect based on brief signal fluctuations.
Before we move on, we need to standardize the language around that link. What exactly are we regulating here?
We are regulating the command and control link, the C2 link. This is the secure two-way digital pathway, and it's composed of two critically distinct vectors. You have the uplink, which carries the operator's commands and mission updates to the aircraft, and then you have the downlink, which streams critical telemetry position data, aircraft status back to the operator and the ground control station.
That distinction, uplink versus downlink, that's much more than just terminology, isn't it? They represent fundamentally different hazards.
Oh, they absolutely do. If you lose the uplink, you can't send commands anymore. The aircraft is now operating autonomously based on its last instruction. That's an immediate risk to the mission and potentially to airspace if the aircraft deviates. But if you lose the downlink, you stop getting telemetry back, the pilot has suddenly lost situational awareness. They don't know their aircraft's precise position, its altitude, or its battery state.
Yeah.
This is a severe threat to ground safety. So Part 108 demands that the system define independent link timeout procedures for both scenarios, because the appropriate safe predetermined action might be different depending on which link failed.
Okay, so if that C2 link, uplink, or downlink goes below a minimum performance standard for a specified period, what's the exact mechanism that triggers the failsafe?
That is the link timeout. It's the precise, defined threshold, a specific duration, often measured in seconds, and a set of conditions like sustained low signal strength or unacceptable latency that the aircraft is programmed to recognize as a hard C2 failure. And that triggers the automatic contingency response. And this threshold can't be arbitrary. It has to be demonstrably linked to the risk tolerance of that specific operation.
And the response itself is the playbook, the rule the aircraft has to follow.
That's the Safe Predetermined Action, or SPA. This is the predefined, standardized, autonomous action the aircraft must execute when that link timeout is reached. The FAA anticipates standardization of these SPAs based on the type of operation and the risks involved. So actions like route-based RTH entering a loiter or hold pattern or executing a controlled landing.
You stressed earlier that the SPA must be deliberate. This moves the conversation away from a generic just turn around and into some highly tailored planning. Why is that mandate for deliberate action such a key feature of Part 108?
Because the entire premise of BVLOS relies on the operator proving they have mitigated every foreseeable risk. A generic RTH might solve the air risk, but it could create a massive, unforeseen ground risk. So the SPA has to be mission and geography specific. It has to be designed to minimize the ground risk exposure in that exact operational area, considering terrain, obstacles, and population density.
Give us a detailed example of how the choice of SPA just flips based on the environment.
Okay, consider 3 environments. First, a linear inspection mission along a remote, low-density gas pipeline corridor. If the link fails there, the ground risk is minimal, and the priority is recovering the asset efficiently. So here, a route-based RTH along that pre-cleared corridor is highly appropriate. It gets the aircraft back to the launch site fast.
Mike, contrast that with an urban core, our case file 2.
In a dense urban core, ground risk is paramount. A 5-mile RTH might involve flying over schools, major highways, obstacle canyons. Here, distance is the enemy, so the priority shifts to containment. The safest action is often a local hold pattern, immediately followed by a strategic descent and a controlled landing into a pre-approved small emergency zone. The SPA here prioritizes reducing exposure time over distance traveled.
And finally, what about operations around critical infrastructure? Maybe a major airport's perimeter fence or a refinery where striking the asset itself is an unacceptable risk.
That demands immediate cessation of flight activity, no question. The safest action there is an immediate controlled landing at a designated, pre-approved recovery box located inside the safe perimeter. You reduce the risk to the critical ground asset faster than you could by attempting any transit maneuver. The core principle Part 108 enforces is that the best SPA is not universal, it's context dependent. It has to be planned, configured, and tested before the operation ever begins.
So we've defined the core actions, RTH, hold, descent. But now we have to connect the dots to the system integrity. You mentioned the failsafe ecosystem. This means the failsafe's success depends not just on the aircraft's programming, but on the operator's entire logistical and planning framework.
Exactly. And the foundational philosophical document governing this whole framework is what we call the 5P contingency rule. This rule is non-negotiable for achieving Part 108 operational maturity because it governs the integrity of every single safe, predetermined action we just discussed.
Okay, let's dedicate some time to this. It sounds important. What are the 5 Ps? And more importantly, what's the practical operational consequence if an operator violates each one?
So the first P is predefined. The action must be written down, configured, and subject to version control. If an operator feels this, they're effectively improvising in the face of failure. In a regulatory context, this results in an immediate grounding because there is no auditable record of the safety procedure.
Okay. The second P, and this one seems crucial for integrating into the national airspace system, is predictable.
Yes. Predictable means the system must exhibit the exact same behavior every time the trigger is hit. And this predictability must be legible to the entire operational team and increasingly to external airspace management services like UTM. If an operator violates predictability, say, the RTH altitude changes based on a minor software update, it undermines the trust required for scalable BVLOS. It becomes impossible for the FAA to grant wide area authorization if the contingency response is unstable.
The third P, proportionate. How do operators gauge the appropriate response level?
Proportionate means the response has to match the assessed ground and air risk. If a BVLOS flight is over an unpopulated desert, a long-distance RTH is proportionate. If the flight is over an oil refinery, an immediate controlled descent to a safe zone is the only proportionate action. The violation here is often choosing the action that benefits the asset recovery, like trying a long RTH to save the drone over the action that minimizes third-party risk. And that's immediate landing. Part 108 forces that prioritization of risk mitigation.
And the fourth P, provable. This speaks directly to the testing requirements.
Provable means the action must be tested and validated in representative environments. It's not enough to test RTH in a lab or under perfect signal conditions. You have to test it in areas with known radio frequency noise, intermittent signal loss, and high winds. Violating provable means your safety case is purely theoretical. You can't guarantee performance under the actual stress of the mission.
Okay, and the final P, published.
Published means it's included in all operating instructions, training materials, and pre-flight briefings. This closes the loop. The human element must be as predictable as the automation. If the procedure isn't published, the operator can't be trained, and the operator's response might conflict with the automation's behavior, creating a very dangerous conflict.
That 5P rule is a fantastic framework. Now let's look at the hidden pillars of this failsafe ecosystem that support these actions. Let's start with power.
Right. Pillar 1, battery health and energy discipline. This is the #1 overlooked failsafe element. Everyone focuses on the C2 link, but RTH logic is useless if you don't have the energy to execute it. The NPRM requires that operators implement a rigorous battery monitoring program that goes beyond just mere percentage readings to assess the physical state of health, or SOH.
So SOH accounts for degradation, how many cycles the battery's been through, its ability to deliver peak current, that sort of thing.
Exactly. Factors like extreme temperature exposure and cycle count degrade a battery's internal resistance, which means the available energy on paper might not be the deliverable energy when the system needs it most, like climbing to an RTH altitude against a headwind. If degradation turns your planned reserve into a fiction, your RTH distance shrinks and your proportion of risk just explodes.
So the automation needs to build hard energy gates into its logic to ensure the SPA is actually viable right now.
Absolutely. The system needs to enforce automatic downgrade logic based on sophisticated, predicted battery capacity modeling the energy penalty for the return flight against ambient conditions. The thresholds have to be enforced. RTH is feasible. Divert to the nearest alternate only. Or the final gate, immediate controlled landing. If the battery drops below the minimum threshold required for the near safe action, the automation has to prefer safety containment over completing any further transit.
Let's shift gears from the physical to the digital. Let's talk cybersecurity.
Pillar 2, cybersecurity as a fail-safe risk multiplier. Part 108 includes explicit requirements to protect C2 networks, devices, and data. And you ask, why is this a fail-safe issue? Because modern lost link events are just as likely to be caused by intentional interference or network intrusion as they are by, terrain obstruction.
So a low-cost, off-the-shelf jammer deployed near the ground control station could induce a fleet-wide lost link event, and it would look just like an RF failure. The system needs to respond identically, regardless of the cause.
That's the critical linkage. Operators must train their teams to treat jamming, spoofing, or intrusion as operational hazards that impact the C2 pathway. Your mitigation tree is simple. Detect the anomaly like an unexpected sudden signal drop combined with a healthy link budget elsewhere shift immediately to the safe predetermined action, the SPA, and simultaneously log the event for forensic analysis and mandatory reporting. For Part 108, cybersecurity is not an IT issue. It's an immediate, mission-critical flight safety issue that requires a predictable, automated response.
And finally, the environment, the one thing we can't control.
Right. Pillar 3, weather limits and environmental escape logic. Compliance with manufacturer operating instructions is standard, but the NPRM adds explicit concern over specific hazards like icing, heavy snow, and high winds, as these dramatically alter the aircraft's aerodynamic profile and its energy consumption.
Seems like the fail-safe design has to be dynamically linked to the environment then.
It changes everything. For instance, the system needs to calculate the RTH time not just on distance, but on predicted wind at the RTH altitude. If the winds aloft exceed the manufacturer's limit, attempting RTH at that altitude is dangerous. The system must possess environmental escape logic, the capability to identify an environment beyond its limits and execute a safe, pre-planned exit. This might mean descending into a less windy layer or diverting to the nearest alternate immediately before a front arrives. This just reinforces the proactive nature of the failsafe ecosystem.
Okay, now we can structure the specific failsafe action, starting with RTH. If we're moving beyond the simple shortest path home, we have to recognize why that direct line approach is such a significant stealth risk.
The shortest path home is a risk because it's purely geometric. It operates in a vacuum, ignoring the complexity of the ground and air environment. That direct vector can suddenly cross new population centers, cut through taller obstacles erected since the mission was planned like temporary communications towers or cranes, or, most critically, deviate from the pre-assessed and approved communication coverage corridor. You might be leaving a good coverage area and flying directly into a known RF dead zone in your panic.
So the goal of the recovery path shouldn't be speed, it should be hazard minimization.
Precisely. This is why the best practice for Part 108 is route-based RTH. The aircraft returns along a pre-cleared corridor or a designated return lane. This corridor has been pre-assessed for minimal ground risk, obstacle clearance, terrain adherence, and verified C2 link availability. The policy has to minimize third-party risk and keep the aircraft within the planned safety envelope.
To structure this approach, we need a clear methodology for destination selection and triggering. We need to introduce the ROAD checklist.
This mnemonic helps operators ensure they cover all the necessary planning steps. First, you have to lock the trigger. This is the non-ambiguous signal, the link timeout, the C2 service anomaly, or a sudden severe drop in system health, like a navigation confidence drop that initiates the RTH sequence. And we have to be clear on whether the trigger requires both uplink and downlink failure, or just one.
Okay, so ROAD starts with R.
R stands for route policy. This dictates that RTH must follow a pre-approved corridor or lane, ensuring predictable movement that minimizes ground risk and adheres to necessary terrain and altitude constraints. This policy is really key to scaling operations.
And O is for awareness.
O is for obstacle people-aware altitude strategy. The RTH altitude isn't just fixed. It has to be dynamically calculated to ensure clearance above known and potential obstacles, avoid conflict with other airspace users, and, where possible, minimize unnecessary overflight of high-density population areas. It's a dynamic risk management layer.
Okay, now A addresses the single point of failure problem.
Right. A is for alternate landing hierarchy. You can never, ever rely on a single home point. Your destination ladder has to be layered. Primary home, the launch site. Mission home, a safer mid-route recovery point defined for a long mission. And then pre-designated alternate landing area A and B. Part 108 expects the operator to have explicit agreements and validation for safe landing capability at all of these locations.
Planning 4 alternates per mission sounds computationally and logistically intense. What are the operational compromises operators typically have to make when defining these sites? Especially regarding, land access and the necessary infrastructure.
That's where the challenge meets reality. Logistically, you can't always secure 4 fully staffed, instrumented landing pads. The compromise is often in the level of validation. So, primary home is fully instrumented. Mission home might just be a secure field with defined access. Alternates A and B might be selected based purely on geographic risk mitigation, a known safe patch of low-density land, and the automation is validated to execute a less precise landing there. The regulatory challenge is proving that even the least instrumented alternate is still safe for a controlled emergency landing.
And finally, D.
D is for decision gates. This ties back to the energy and confidence we discussed in Section 2. The RTH logic must be constantly gated by current energy levels, link confidence, and crucially, PNT, position, navigation, timing, confidence. If any of those key health metrics fall below the required threshold for a successful RTH, the system must immediately downgrade its action to divert or land closer.
Let's pull on that PNT thread. RTH requires extremely high-fidelity PNT to navigate back without human intervention. So how does the aircraft detect that its PNT confidence is dropping? And what does it do about it?
This is where we get a little technical. PNT confidence drops are detected by the sensor fusion system. The aircraft isn't just relying on GNSS like GPS or Galileo. It cross-references that GNSS data with its internal systems, specifically the Inertial Measurement Unit, IMU, and often a magnetic sensor or vision-based positioning systems. If the GNSS signal suddenly becomes erratic, if there's a huge spike in what we call positional error covariance, which might indicate spoofing, jamming, or heavy multipath, which is signal bouncing off buildings, the internal navigation filter registers a drop in PNT confidence.
So the system recognizes the data is untrustworthy.
Exactly. And when confidence drops, the automation has to immediately treat it as a co-failure with the lost link. The system might revert to what's called dead reckoning, relying solely on IMU data for a short period, or if the drop is severe, it triggers an immediate failure mode that bypasses RTH entirely. It defaults to a local hold or controlled descent because attempting a long transit without reliable PNT introduces just an unacceptable level of navigational uncertainty. The validation imperative demands that operators test RTH under these conditions, simulating GNSS degradation to prove the transition logic works.
RTH is about mobility. The next step on the ladder, the holding pattern, is about stability, freezing the risk footprint. What's the operational purpose of the hold in a Part 108 context?
The hold is a bridge action. It is never the end state. Its primary purpose is to stabilize the aircraft's state and ground risk exposure immediately upon recognizing the link timeout. It buys the system and the remote crew time. Time to decide. Time to attempt to regain link, confirm air traffic state, reassess battery capacity against current wind, and figure out the safest path forward.
A hold can't just be a generic loiter, though. To be predictable, it needs geometry.
Yeah.
So what is the standard structure for a Part 108 grade hold? We use the BOX checklist.
The BOX model defines the boundaries and duration of this bridge maneuver. B is for bounded volume. The hold must be geofenced, strictly altitude banded, and time limited. It's a predictable airspace bubble defined by the ground risk assessment. And that volume has to be pre-cleared and conflict minimized, anticipating that this predictable behavior has to be legible to the entire airspace management ecosystem.
How does that bounded volume become legible to the wider airspace ecosystem, like the UTM systems or ADSPs, the approved data service providers?
This is a critical regulatory integration point. To be Part 108 fluent, the bounded volume and the predicted action must be published digitally. This typically happens via an application programming interface, an API, using standardized geofencing formats. For instance, the system communicates to the ADSPs that aircraft X is now entering a contingency volume centered at Y altitude Z with a maximum duration of T minutes. This allows the UTM system to manage separation for other crewed or uncrewed users who might be operating nearby, relying on that published, predictable behavior.
So the hold is active for a set amount of time defined by O.
Right. O stands for Observed Health and Link Recovery Window. This is your decision gate. The hold lasts only long enough to evaluate the situation. For instance, the system might be programmed to hold for 90 seconds while attempting link restoration and simultaneously recalculating energy feasibility for RTH.
And if that window expires, the system has a transition. So X marks the termination point.
Correct. X is for X out to RTH land when threshold hit. The hold must have a forced transition to the next safest step. If the time limit expires, or if health parameters like battery level or PNT confidence drop below the required threshold during the hold, the system is forced to transition to either RTH, divert, or controlled landing. The autonomy is making a decision on time-limited data.
This brings us to the final, most decisive step in the failsafe ladder: emergency descent. If RTH is about transit and hold is about stability, descent is the precision tool for risk reduction when all else fails. It sounds like the absolute last resort, but it still has to be planned.
It is the response to reduce risk exposure time when remaining airborne presents a greater hazard. It's rarely triggered by lost link alone. Emergency descent is typically a response to compounded failures. So, lost link plus severe weather exceedance, or lost link plus confirmed navigational uncertainty, or a low battery breaching that immediate landing gate.
What's the professional move that separates a controlled descent from an uncontrolled crash?
It's defining descent boxes. Emergency descent is safe only if you pre-design and pre-validate these microzones. A descent box is a pre-validated microzone with a known low-risk ground footprint. So, low population, minimal obstacles, and verified ground access for recovery. This is what allows for a precision, rather than a panic, landing.
Okay, let's structure the planning for that precision tool with the SAFE checklist.
S is for selected ELZs, emergency landing zones. These have to be pre-validated and integrated into your ground risk model. They are the physical targets for your descent boxes.
And A.
A is for altitude obstacle-aware profile. The descent can't be ballistic. The logic has to apply strict rate limits appropriate to the aircraft type and follow an obstacle-aware path, ensuring power is maintained for control surfaces throughout the entire descent.
F.
F is for failure triggered, not improvised. This sequence is an automated, repeatable, and standardized response. It removes the human error factor during a high-stress, multi-failure event. E is for energy PNT considered. The descent decision logic has to confirm that the aircraft has sufficient power to manage the descent profile and sufficient PNT fidelity to target the descent box accurately. If PNT is completely gone, even the descent becomes riskier. This complex descent logic is part of a broader discontinue flight capability required by Part 108 for various system malfunctions, and it has to be highly protected against any inadvertent activation, often requiring redundant activation pathways like an encrypted signal or a dedicated protected hardware switch.
We've covered the components, now we apply them. The true test of operational maturity is choosing the right failsafe action for the right context. The best failsafe is entirely context-dependent, driven by the unique ground risk and environment. Let's run 3 detailed case files to see how the choice of SPA changes.
These scenarios force a calculated trade-off between speed, containment, and energy preservation.
Okay, case file 1. Rural power line corridor, long-distance linear inspection flight over sparse population, but with intermittent link coverage and mixed terrain.
The key hidden threat here is automation thrash. Because the corridor is long, you have predictable RF dead zones like deep valleys or terrain masking. If the system is too sensitive, the aircraft will bounce repeatedly between mission flight and RTH because of these micro dropouts. This thrash wastes energy, puts structural stress on the aircraft, and creates unpredictable behavior.
So if direct RTH is the goal, what operational bias do we implement to prevent that thrash?
We bias towards stabilizing first. The action logic has to involve entering a pre-cleared hold bubble immediately upon link degradation, not link timeout. This time-capped buffer allows the system to stabilize and confirm the severity of the loss. If the timeout trigger is then confirmed, the system transitions to a route-based RTH along a parallel pre-assessed return lane that is slightly offset from the power line infrastructure, reducing the risk of collision with the asset during the automated maneuver.
So the hold bubble enforces that graceful degradation you mentioned earlier.
Yes.
It forces a mandatory pause for reevaluation before committing to a costly, lengthy RTH.
Exactly. The success of this rural mission hinges on making sure the aircraft's footprint, whether flying or recovering, stays predictably inside that narrow planned corridor.
All right. Case file 2. Urban delivery. High density environment. Complex obstacle fields. High pedestrian exposure. This forces an entirely different risk hierarchy.
The hidden threat here is the density-weighted risk. In an urban canyon, a straight-line RTH, even if it's technically feasible, might cross a high-density area like a shopping district or a major intersection. The risk created by the RTH maneuver itself is higher than the risk of stabilizing immediately.
So the bias flips toward containment, even if it means sacrificing mission completion.
Absolutely. Tight hold is the safest initial response. The pro-level operational move here is deploying a vertical layering strategy. The transit, hold, and descent activities are assigned different segregated altitude layers. And crucially, the system has to rely on pre-validated descent boxes as micro-targets. The action logic says, if link timeout and an energy breach low battery occur simultaneously, the system uses emergency descent to target the nearest pre-validated box.
And this raises a significant practical and regulatory challenge. How do operators get clearance to designate private rooftops or utility yards as descent boxes in dense urban areas? That requires extensive site access agreements.
It absolutely does. This is the biggest logistical hurdle in urban BVLOS. You can't just designate private property as an ELZ. Operators have to secure explicit site access agreements, often involving local ordinances, property owners, and sometimes first responders. If access can't be guaranteed, the operator must carry a higher risk tolerance for landing in public space or limit operations to areas where safe recovery boxes, like pre-cleared public parks or fenced areas, can be reasonably accessed. The operational choice here is entirely driven by logistics and regulatory clearance. The goal remains to shrink uncertainty fastest by minimizing lateral movement.
Okay. Case file 3. Coastal wind farm inspection. Flights over water. Massive structures coupled with unpredictable wind gradients.
The hidden threat is not just the lost link, but the wind mismatch leading to exaggerated battery drain. Coastal areas, especially over water, present dramatic wind shifts between the surface and higher altitudes. If the return leg encounters a sustained headwind that wasn't accurately forecast or calculated, RTH can become energy impossible much faster than the autopilot expected. This scenario punishes optimism.
So the primary bias has to be on energy realism, using wind-aware energy modeling to govern all failsafe decisions.
Correct. The system needs constant recalculation of the energy penalty. The action logic involves leveraging altitude-banded holds. If the link degrades, the aircraft can shift into a predefined altitude layer that has the least punishing wind characteristics, conserving critical energy reserves. If the energy feasibility calculation for RTH fails due to the sustained wind penalty, the logic must force a divert to a nearer, safer alternate landing point like a controlled maintenance barge or a nearby coastal recovery site, instead of attempting a heroic RTH that will guarantee ditching the aircraft far from safety.
These case files really demonstrate that failsafe integrity is built on pre-planning. Part 108 makes it clear that the operator has obligations that go far beyond what the manufacturer certifies. This is the realm of operational maturity.
This is where safety becomes a shared burden. The manufacturer provides the certified airframe and flight control capabilities, but the operator is responsible for ensuring the real-world performance matches the safety case. Operators have to ensure C2 coverage and availability in the operating area, proactively resolve interference before the flight begins, designate those alternate landing sites with required access, and crucially validate that the lost link procedures work in that specific environment.
And Part 108 operational maturity isn't a one-time stamp of approval. It's a continuous, recurrent process.
Absolutely. The rule proposes capturing operational data link strength logs, battery health trends, flight path deviations for continuous trend analysis and failure identification. This makes lost link mastery a recurrent competency. Teams have to prove recency of operation, often through regular simulator training or flight cycles, ensuring the human operator's response to the automated SPA remains standardized and predictable.
And that data analysis helps spot the subtle but dangerous operational traps. Let's talk about the inoperative equipment trap. How can a legally permissible inoperative sensor still undermine the overall safety of the fail-safe system?
This is a classic nuance of complex systems. Suppose your aircraft is approved to fly with a single magnetometer. The compass sensor inoperative, provided the GNSS is fully functional. Legally, you can fly. However, if the GNSS system then experiences signal degradation, a co-failure, the loss of the magnetometer means the aircraft cannot accurately maintain its heading or attitude during the automated RPH. It's lost a critical backup sensor for the navigation filter. This loss of input renders the auto RTH altitude selection or emergency descent logic completely unpredictable, turning a non-hazardous inoperative sensor into a critical risk multiplier during a contingency. The operator has to judge this operational nuance and ground the aircraft until the sensor is fixed.
Before we wrap up, let's look at the global context. Part 108 is the U.S. approach to scalable BVLOS. What is the comparable regulatory philosophy elsewhere?
The closest, most philosophically aligned parallel is found in Canada's Level 1 complex operations. Part 108 is the U.S. effort to create a standard, scalable framework for routine BVLOS in the NAS, moving away from waivers toward a predictable rule set.
And Canada's system mirrors this risk-based maturity.
Yes. Canada's Level 1 complex pathway is built around strict requirements for lower-risk BVLOS in uncontrolled airspace. It requires a specific pilot certificate and an RPAS operator certificate, an RPOC. The fundamental shared goal between the FAA and Transport Canada is their obsession with predictable contingency behavior. Both frameworks demand risk-based decision-making and, crucially, managing risk at the operator system level, not just relying on the skill of an individual pilot. If you train for Part 108's ROAD criteria, you're already meeting the predictive planning required for Canada's complex operations. Structured safety is truly the global language of BVLOS maturity.
Okay, let's bring this home and synthesize this deep dive. We began by viewing lost link as a moment of potential panic, but we've redefined it entirely. Lost link is simply a moment of pre-calculated, predictable transition within a tightly managed operational envelope.
Exactly. The failsafe strategy is built on the trinity of actions: route-based RTH, bounded hold, and precision descent. But that trinity is powerless unless it's backed by the integrity of the planning ecosystem, rigorous SOH battery management, proactive cyber defenses, and high-fidelity PNT reliability.
The Part 108 shift is mandatory. moving from ad hoc reaction to deliberate, predictable, and provable contingency planning.
And to lock in the key steps for designing that robust failsafe system, we give you the architecture for failsafe strength, THREAD.
Okay. Key stands for timeout defined, clearly addressing the different risks posed by uplink and downlink loss.
H is for hold volume bounded and time limited, ensuring containment rather than uncontrolled drift.
R is for return corridor planned, utilizing pre-cleared low-risk routes instead of the potentially hazardous shortest path home.
E is for emergency descent tied to selected safe alternates, those pre-designed, pre-validated descent boxes.
A is for automation consistent across the entire flight envelope, meeting that 5P mandate for predictable behavior every single time.
And finally, D. And finally, D is for data and cyber defenses baked in, acknowledging that system integrity has to be protected from external interference and providing the data needed for continuous recurrent competency.
So if you take one clean, memorable line away from this entire deep dive, let it be the encapsulation of the entire philosophy of Part 108 BVLOS safety. Lost link isn't the emergency. Your unplanned response to lost link is.
That is the principle that governs the future of automated airspace. Every single element of the Part 108 rule is designed to replace human improvisation with machine predictability.
So we encourage you to look at every complex automated system you rely on, whether it's a self-driving car, an industrial robot, or a BVLOS aircraft, and consider where its predictability might fall apart. What are its predefined limits? What happens when the connection is intermittent? That line between predictable behavior and catastrophic failure is where the next generation of safety design will be found.
That's a wrap on today's mission, Commander. See above, go beyond, get ahead. For more training, tools, and intel, head to skycommander.ca. If you learned something new, share it, subscribe, and leave us a 5-star debrief.